Okay. Good afternoon, all. In From last few lectures, we are discussing related to the heat treatment process, and that heat treatment process will that related to the steels only. In the previous lectures, we have finished the annealing, normalizing, and hardening. Three heat treatment processes we have learned, or we have discussed that part along with their purpose, then their procedure, then their subtypes, and what are their different applications for each heat treatment process will be used for different types of the steels. It may be low carbon, medium carbon, or high carbon steel, or alloy steel. Okay. Then according to the modification needed in the properties, we can choose the heat treatment process, and that we have seen the annealing, normalizing, and in the previous lecture we have conducted the lecture on the hardening heat treatment process on the steels along with its different subtypes. Now we will move towards the next part. Before starting the next heat treatment process, that will be the tempering. Yeah, this is the fourth heat treatment process. This is the tempering heat treatment process. Before starting this tempering heat treatment process, uh, first we will discuss related to the what is the meaning of retained austenite, and then what is the effect of that retained austenite on the properties of the steel. Then in the next point, we will discuss related to the methods which are applied, or which methods you can use for elimination of that retained austenite. There are three methods. We will discuss all three methods in today's lecture only. And then after completing this retained austenite part, and then we will move towards the fourth heat treatment process, that is the tempering. And we will start one by one. First, we will start with the retained austenite. Then, what is the meaning of retained austenite? Okay, retained austenite, it is also known as the untransformed austenite. Okay, this retained austenite term, for understanding this, what is the meaning of retained austenite? You have to take the reference of the hardening heat treatment process. Okay, this is your hardening heat treatment process. I will take any one example. I will take this time quenched hardening process. In this hardening process, we want to improve the hardness of the steel, then its wear resistance and cutting ability of the steel. For that, we are performing the hardening process. Now, in this hardening process, the first step will be the heating. Then we are providing some holding time or soaking time, and after that we are cooling it up to room temperature, so that whichever austenite is present at the higher temperature zones, it will get transformed to the martensite. Okay, we are transforming this a is nothing but the austenite from higher temperatures, and we are cooling it to the room temperature, or sometimes we can go below the room temperature also, and we will end up with the martensite. Okay, so this is the general hardening process. But during this hardening process, at the end, in some kind of the steel, suppose high carbon steels are there, then their martensite finish temperature, martensite transformation finish, or martensite transformation complete temperature is below room temperature, or sometimes it will be in the negative temperature zone. So it is almost impossible to transform all austenite to the martensite. Okay, all austenite will not get transformed to the, I mean, suppose here 100% austenite is there, that 100%, you will not end up with getting the 100% martensite. You will end up with getting 90%, 95%, or 80% austenite, martensite. Then whichever amount of austenite which remains at the room temperature also, or in the final structure, that austenite will be termed as the retained austenite. Okay, this is the retained austenite. What is the aim of our hardening process? This austenite we want to transform it to the 100% martensite, but at the end we will end up with some austenite as it is at the room temperature also. Here austenite will be at higher temperature, and at a room temperature martensite is needed, but this austenite, some amount of austenite, 5%, 10%, like that, or 20%, sometimes 30, 40%, will remain as it is, means it does not get transformed to the martensite. It will be termed as a retained austenite. If this austenite will remain as it is at that the last phase, that is at the room temperature also, then it will be termed as the retained austenite. Okay, okay, that I have mentioned here also, that is austenite that does not transform to martensite upon quenching is called as the retained austenite. Okay, quenching is nothing but the cooling, or you can say that during the hardening process, on the austenite which remains as it is or does not transform to the martensite, it will be termed as a retained austenite. Then the next is the this austenite amount of the austenite will be distributed, or retained austenite will present in the large amount at, you can say that, near the surface it will be very less, and at the center of that component it will be at the larger quantity. Okay, that is explained in this point, that is the amount of retained austenite, it will vary from center to the surface of the component. And if you observe the surface, then amount of the retained austenite will be very much less at the surface. And if you observe the center of that component, then amount of the retained austenite will be in very larger amount or larger quantity. Then why it is happening, why the amount of retained austenite is very less at the surface or near the surface, and why it is more at the center or near the center? Now, for the reason behind this is because whenever we are doing the cooling from the higher temperature zones, surface will get cooled very early. Okay, surface is cooling very earlier as compared to the center. Okay, at surface will come in contact with that cooling medium very early, that's why it will get very cooled early as compared to the center. That's why at the center amount of the retained austenite will be more, amount of retained austenite will be more, and near the surface or at the surface it will be very less, because surface cools very fast or at the early stage. Then now this retain amount of retained austenite also depends on the quenching temperature. Here quenching temperature refers to the higher temperature range from which we are taking that component out from the furnace, that may be 900 degrees Celsius or 850 degrees Celsius, like that. And what will happen due to this higher quenching temperature, temperature differences will be large. We are taking, suppose one component we have taken from 800 degrees Celsius, and we have cooled it to the 30 degrees Celsius room temperature. Okay, and one component we have heated at the 900 degrees Celsius, and we are quenching it up to room temperature, that is 30 degrees Celsius. Means whenever temperature is higher, quenching temperature is higher, then thermal stresses will be more. Whenever quenching temperature is higher, it results in the more thermal stresses due to the larger temperature difference. And due to this larger temperature difference, amount of that retained austenite increases. Okay, so these are some concepts related to the retained austenite. What is the retained austenite? Then what are the factors affecting, means depending on which factor you will, amount of that retained austenite will change, depending on the quenching temperature it will change, and depending on the you can say that at the surface it will be different, and at the center of that component it will be different, that its distribution will be different, that retained austenites distribution will be different. I will repeat this part again. I will summarize it. What is the meaning of a retained austenite? The austenite which does not transform to the martensite upon the quenching, that will be termed as retained austenite. Sometimes in the high carbon steels, their EMF temperature, that is martensite finish temperature, is below room temperature, or it is in the negative temperature zone. That's why it is almost impossible to transform the austenite to the 100% austenite to the 100% martensite at the room temperature. Some amount of austenite will remain as it is at the room temperature also. It will be termed as a retained austenite or untransformed austenite. Then uh, related to its distribution, amount of the retained austenite will be very much less at the surface or near the surface, and it will be in very large quantity at near the center or at the center, because surface will get cooled initially and center will get cooled in the later half of the cooling process or quenching process. Then the amount of retained austenite depends on the quenching temperature. As quenching temperature is more, then difference between the temperature will be more. Okay, difference between the temperatures will be on the higher side. Due to this, what will happen, thermal stresses will get created, and due to the large amount of the thermal stresses, retained austenite will be also in the large quantity. So this is related to the retained austenite or untransformed austenite. What is the meaning of retained austenite? Then what are the factors affecting the amount of the retained austenite? Then after this, we will see we will move towards the next point, that is the what is the effect of this retained austenite. Now, effects of the retained austenite, here I have combined both the means there are some advantages of retained austenite and there are some disadvantages also. I have combined that advantages and disadvantages in the single slide here. First 2 points, that are the advantages, you can write in the advantages also. Advantages of the retained austenite, the first 2 points. And I will explain it in short. The first 2 points you can explain in one point also, means due to the whenever amount of retained austenite is there, as austenite is soft, malleable and ductile phase, austenite is soft, malleable and ductile phase, it will improve the softness or ductility of that steel component, and it will reduce its tendency of the cracking. Okay, that point is separated in here, that single point is separated in the 2 points depending on the percentage of the retained austenite. Here, whenever retained austenite is up to 10%, it will reduce the tendency of the cracking. Okay, it will reduce the tendency of the cracking during the hardening process. And whenever amount of retained austenite is up to 30 to 40%, then you can conduct some cold working operations on that steel component, because it will improve the ductility or softness of that steel. In short, you can say that retained austenite, it will improve the ductility, uh, or you can say that it will improve the malleability, so that it will reduce the tendency of the cracking, and you can perform different cold working operations very easily on it, on that kind of the steel component whenever there is some amount of retained austenite is there. Okay, so these are the advantages. Okay, due to that retained austenite, like softness, ductility or machinability will get improved, and you can able to perform some cold working operations, and it will be performed without cracking, or tendency of cracking will get reduced, and you can perform some hardening operations on it also. Then next point is the remaining 3 points, these are the disadvantages. What are the These are the disadvantages of the retained austenite or untransformed austenite. These are the disadvantages. Now, due to this retained austenite, as we have discussed in the earlier points, that it will improve the ductility. And as ductility is improving, what is the disadvantage related to it? The retained austenite will reduce the hardness of that hardened steel component. If during the hardening process, if you have performed hardening process on one steel component, and at the end, uh, if suppose some amount of austenite is there, along with some martensite, some 5 to 10% austenite is there, then its hardness will be in the decreasing order, or its hardness will get reduced, or you will be not able to achieve your targeted hardness value. Due to the retained austenite, it will reduce the hardness. Then sometimes this retained austenite increase the brittleness of the steel. Now, why here brittleness of steel is increasing? Because whichever austenite is remained there at the room temperature. Due to some plastic deformation process, it will get transformed to the martensite. Okay, due to its plastic deformation, it will get transformed to the martensite, and due to this transformation, some internal stresses will get created here. Okay, some internal stresses will get created, and due to that internal stresses, that material or that steel will become brittle in nature, and with very small amount of the shock or a very small amount of the load, it will get break. Okay, so these are the two disadvantages, that is, it will reduce the hardness and it will increase the brittleness due to a transformation of austenite to martensite by plastic deformation. Okay, and due to this plastic deformation, internal stresses will get increased, and due to that, material will become brittle in nature, that steel will become brittle in nature. Then the third effect, or you can say that the third disadvantage, is that due to this retained austenite, whenever there is a retained austenite, and as time passes away, slowly this retained austenite which is present in the steel, it will get transformed to the bainite. All these transformations will occur at the room temperature, and this will occur, means it will directly proportional to the time. As time is passing away, whichever retained austenite is there, it will get transformed to the bainite, and due to this transformation from austenite to bainite at room temperature, some linear expansion will occur. Linear expansion in the sense, there will be some changes in the dimension of the that component of steel. There will be some changes in the dimensions, that will be termed as the linear expansion, and that linear expansion will occur in proportion to, here I have mentioned it, 0.0001 centimeter per centimeter. This much change in the dimension will take place whenever you are having 0.3% retained austenite. Okay, for 0.3% retained austenite, for every centimeter, this much centimeter change will occur, or linear expansion will takes place. And why it is happening? Because of that retained austenite only, and that whenever that retained austenite transform to bainite, it will result in linear expansion. Okay, so these are some disadvantages. Okay, I will summarize it in the short effect of the retained austenite. It has some advantages and it also has some disadvantages. What are the advantages of retained austenite? Due to this retained austenite, as austenite is soft, malleable, and ductile phase, it will improve the ductility of that steel component, and you will be able to perform the different code working operations whenever that retained austenite is 30 to 40%. And if that retained austenite is only up to 10%, then you can perform the hardening without cracking, means tendency of cracking will get reduced. So these are the advantages. Then in the disadvantages, this retained austenite will reduce the hardness of the hardened steel. Then this retained austenite, if suppose it get transformed to martensite by plastic deformation, it increases the internal stress, and due to that internal stress, brittleness of steel will get increased. And if that retained austenite get transformed to bainite, then some, due to the volume changes, linear expansion will occur in that steel component. So these are the disadvantages. Some advantages are there and some disadvantages are there. And now to so whenever amount is on the upper side or higher side, or suppose you want to improve its hardness, you want better hardness in that particular type of the steel, then you have to eliminate this retained austenite. You have to eliminate this retained austenite to improve the hardness, then its wear resistance, its cutting ability, then to provide the stability to the that particular steel component, you have to eliminate the retained austenite. And to eliminate this retained austenite which is present in the steel component, uh, three methods are used. The three methods will be like this. The cold treatment, it is also known as the sub-zero treatment, then plastic deformation and tempering. These three methods are there to eliminate the retained austenite. Please note down this cold treatment from this elimination of the retained austenite. This cold treatment process or sub-zero treatment, they have asked this just mention, just you have to write down these temperature values. This is the medium used for performing the cold treatment or sub-zero treatment. Just write down these mediums and their temperature range. I will wait for 1 minute here. After writing, please mention that in the chat box that you have completed it. And if you are having any query up to this point, what we have discussed up to within this first 20-30 minutes, retained austenite, what is the meaning of retained austenite or untransformed austenites, factors affecting the amount of retained austenite, and then its distribution in that particular steel component, and what is the effect of the retained austenite on the properties of the steel that we have discussed. Now different elimination methods are there that we will discuss in the next 20-30 minutes. I will wait for 1 minute here. Please note down these temperatures which are provided by with the help of different mediums. We will able to get the different temperature zones. Please note this. I will wait for a few minutes here. After completing, please mention that in the chat box you have completed. And if you are having any query, also mention, you can mention that in the chat box. I will try to clear it. Okay, after understanding what is the meaning of retained austenite or untransformed austenite, then its effect on the properties of the steel, then there are different elimination methods to eliminate that retained austenite. Generally, we are using three elimination methods. First is the cold treatment or sub-zero treatment, then plastic deformation, and the last is the tempering. The tempering is nothing but a heat treatment process we are directly going to conduct on it. Now, the cold treatment or sub-zero treatment. Now, we are getting, or this retained austenite, we are getting this at the end of the hardening process. Okay, at the end of hardening process, if suppose we are getting the retained austenite, immediately the sub-zero treatment should be performed. Read the second point. Sub-zero treatment should be performed immediately after hardening process. Okay, at the end of hardening process, all austenite is not transformed to the martensite. We are getting some retained austenite there. So to eliminate that retained austenite, immediately you have to perform this sub-zero treatment. on the steel component after the hardening process. And how this sub-zero treatment or cold treatment process is conducted. The steel component is cooled to a temperature below its MF temperature. Okay, for some kind of the steels, that is suppose high carbon steels containing carbon more than 0.7%, then its MF temperature, that is marked inside finish temperature, is below that temperature. Sometimes it may be in the negative temperature zone. Okay, it may be in the negative temperature zone. Now, whichever temperature zones I have written here, okay, okay, these are negative temperatures. Okay, these are negative -23, -183, -76. Please correct it. These are not positive temperature zones. These are negative temperatures. Okay. Please make that correction there. Okay, these are my negative temperature zones. Now, what we are doing at the end of the hardening process, we are conducting that sample, and we are now the sample we are cooling it below MF temperature, and this MF temperature is generally in the negative temperature zone or very low below the room temperature zone. And depending on the temperatures required, you can use the different mixtures to obtain that low temperature values. Now here different mediums I have salted, but ice plus salt. Now here ice plus salt means you have to take the sodium chloride. If you took sodium chloride salt, ice plus sodium chloride salt, you will get end up with getting the -23 degrees Celsius temperature. If you used ice plus calcium chloride, then you will be able to get -55 degrees Celsius temperature. If you used acetone plus dry ice is nothing but frozen carbon dioxide. Okay, dry ice is nothing but frozen carbon dioxide. If you take the mixture of acetone and the dry ice or frozen carbon dioxide, you will be able to get -76 degrees Celsius temperature. Then you can use liquid gases. Suppose you have used liquid nitrogen, you will able to get 196 degrees Celsius temperature. Then for liquid hydrogen, -253 degrees Celsius temperature. Liquid helium will give you -269 degrees Celsius temperature. Now, simply after hardening component, you have to collect, and using the different mediums, you have to cool it below room temperature. And after that, you have to remove the component from that cooling medium. Then you will get that all retained austenite has been transformed to the martensite. That retained austenite will get reduced. Okay, it will get reduced or it will get eliminated. Now, it is almost impossible to get the 100% martensite at the end. Okay, there may be some amount of austenite. Maximum you
Hello,
will
sir.
end up with 99% of the. Ah, yes.
One student is waiting outside. Please allow.
I'm not getting any notification here.
By mistake, he left the meeting. Please allow.
Wait. Tell him to join. I will join him. I'm not getting any notification here. Hello.
Yes, sir.
I'm not getting any notification. Some.
He says, sir,
Your
failed to join.
notification will come. Okay, okay. I will join him if I got the notification here.
Okay, sir.
I will add him. Okay, till that time, we will continue. We will continue with this session.
Okay, sir.
Okay, okay. Ah, yes. Okay. Ah, I have added him. No problem. We'll continue now.
Okay, sir. Thank you.
Okay, welcome, welcome. No problem. Okay. Now we'll continue with this elimination of a retained austenite. In that, we are discussing related to the sub-zero treatment. Okay. Now here at the end of the hardening process, it is almost impossible to get the 100% martensite. Now, if amount of the retained austenite is more before performing uh, elimination methods for that retained austenite, and in that just we have to keep the cooling below MF temperature, that is the martensite transformation finish temperature, and depending on the type of, and it's suppose higher amount of carbon percentage is there, then this MF temperature will be in the negative temperature zone, and then depending on that temperature range we can use the different mediums. Okay, for different mediums we will get the different temperature ranges, and just at the end of hardening you have to collect that component and you have to uh, dip that component in this medium, whichever medium you have selected, and after providing sufficient time you have to remove that component. Now whenever you are performing or after hardening, you are doing the cooling in the very less temperature or in the negative temperature zone, then due to this what will happen, sometimes here cracking may occur. Okay, here cracking may occur. That's why before performing that cold treatment process, before performing that cold treatment process, it's the last point which I have added here. The last point, to avoid the cracking due to this large temperature differences, before actual cold treatment process, you have to perform some low temperature tempering at 150 degrees Celsius or 107, 175 degrees Celsius temperature zone. 150 to 175 degrees Celsius temperature zone, you have to perform some low temperature tempering on that component to avoid the cracking during the cooling process or sub-zero treatment. And in this way you can perform this cold treatment process. Okay, after the hardening you have to first perform this cold treatment process, and then you have to go to the actual cooling, and you will get the elimination or you will get the results that the retained austenite will get eliminated. And this method is used for elimination of retained austenite from hardened components like tool steels and die steels. There are number of components of tool steels. You can take your different kinds of the tools or different kinds of the dies. Okay, from that you can eliminate the retained austenite by following this procedure. Okay, so this is the cold treatment or sub-zero treatment. And after this, the next method which is used for elimination of the retained austenite is just we are doing the plastic deformation. Okay, this is very simple. Just one point will be there. Just I have mentioned the terms involved in it and few examples. The plastic deformation of the austenite is conducted, and due to this plastic deformation, whichever retained austenite is there, it will get transformed to the martensite. It will get transformed to the martensite. Now, this transformation phenomenon is termed as strain-induced martensitic transformation or deformation-induced martensitic transformation. We are providing some deformation, or you can say that we are creating some strain here. We are inducing or creating some strain. Due to that, what will happen, whichever retained austenite is there, it will get transformed to the martensite, and this phenomenon will be termed as deformation or strain induced martensitic transformation, and that temperature at which this process will occur, it will be termed as, you can see here, this temperature is denoted by the letter md, temperature at which deformation induced martensitic transformation starts. Okay, md. And generally this md temperature is above your ms temperature. Here that is also mentioned in this point, above ms temperature. Generally this md temperature means temperature at which deformation induced martensitic transformation. Simply you can say that temperature at which austenite transformed to martensite by plastic deformation, that will be termed as md, denoted by letter md. This is deformation, d for deformation, plastic deformation. Then this process of elimination of retained austenite is plastic deformation process. It is used for eliminating the retained austenite of which is present in the high carbon steel components, then low and medium carbon high alloy steels. Okay, in the high alloy steels, you can simply write high carbon steel and high alloy steels. From that we can eliminate the retained austenite by conducting this plastic deformation process. Then last method of elimination of this retained austenite, just perform the tempering heat treatment process. By performing the tempering heat treatment process on the hardened steel component, now this tempering heat treatment process is performed below A1 temperature, and after sufficient amount of temp, just you have to do the, now this tempering process I will explain it in the next point how this tempering process is conducted. Just try to understand that here, by performing the tempering process on the steel, retained austenite is eliminated from that steel, and this process can be applied to eliminate whenever amount of retained austenite is small, and you can also eliminate the larger amount of the retained austenite from the steel components. Simply the tempering process is the one heat treatment process which consists of heating cycle, then holding time, and the cooling cycle. During this process, after cooling up to room temperature, whichever retained austenite is there, it will get eliminated. And this method can be applied for elimination of smaller amount of the retained austenite as well as larger amount of the retained austenite. Now, how this process is exactly conducted, um, that we will discuss in brief. Whenever in examination they have asked you elimination of retained austenite, just you have to mention these three processes: cold treatment or sub-zero, then plastic deformation, and in tempering process, you have to write these two sentences only. And if suppose they have asked you specifically tempering process, then you have to explain it in brief. Okay, the tempering process will be like this. This is the tempering process. This is the next heat treatment process, and it is the tempering. Uh, First, we will see the purpose of this tempering process. Okay, in examination, they will ask you write the purpose, process, types, and applications of the tempering process. Okay, now first you have to start with the purpose. Now, the main purpose of the tempering process is to eliminate the retained austenite. You can start with the bottom, to eliminate the retained austenite. Whichever retained austenite is there, that can be eliminated, okay, by performing the tempering process. Then here the next purpose is to reduce the hardness and to increase the ductility and toughness. To reduce hardness, sometimes at the end of the hardening process you will end up with the more hardness, or sometimes brittleness will be there in the component. That more hardness or brittleness in the component can be eliminated by increasing its softness or ductility by performing the tempering process. Then another purpose of performing this tempering process, and read the first point, to relieve the internal stresses which are developed due to the rapid cooling. In the hardening process, we have seen that we are doing the rapid cooling from 900 degrees Celsius or 800 degrees Celsius temperature zone. We are collecting the component and directly dipping it into the water. Due to that, what will happen? This is the rapid cooling process. Due to that, what will happen? Larger amount of thermal stresses will get induced in that component. Due to the thermal stresses, what will happen? That component may get failed or some cracks may get developed. To avoid this, you have to eliminate that internal stresses. And to eliminate that internal stresses, you have to perform the tempering process on it. Okay. So these are the objectives of the tempering process. First objective, to eliminate or to relieve the internal stresses which are developed due to the rapid cooling of the steel during the hardening process. And second, to reduce the hardness by improving its ductility. And third, to eliminate the retained austenite. So these are main three objectives or three purposes of performing the tempering heat treatment process. Now, in the next point, how the tempering heat treatment process is conducted. Now, in the same way as we have discussed the annealing, normalizing, hardening, it also consists of three stages. First will be heating cycle, then holding time, and after that the cooling cycle. The first is the heating cycle. Now here the component, steel component is heated in a temperature range of 100 degrees Celsius to 700 degrees Celsius, just below A1 temperature. Okay, just below A1 temperature we are heating it. Now just below A1 temperature, I will take the reference of iron and carbide diagram. Okay, this is the iron carbide diagram. This is this horizontal line. This is A1 temperature line, 723 degrees Celsius temperature. Below this, below this temperature line, we are in the range from 100 to 700 degrees Celsius. This will be our heating zone for the tempering process. And we are heating that component at the 100 to 100 to 700 degrees Celsius temperature, just below A1. That will be our heating cycle. And here we are going to provide 1 to 2 hours holding time or soaking time. And after that, that component is collected and it is cooled in the air medium. Here we are performing slow cooling. Here we are performing slow cooling with the help of air medium. Okay. In this way, this heat treatment is concluded. Now, due to this slow cooling, due to this slow cooling in the air medium, what will happen? Whichever internal stresses are there, it will get eliminated. Whichever retained austenite is there, it will also get eliminated. And depending on the temperature zones, different structures can be obtained here. Now that we will discuss in the types, depending on the tempering temperature zones used, there are three types of the tempering. First is low temperature tempering, then medium temperature tempering, and third is high temperature tempering. These all three types are on the basis of temperature used for conducting that tempering operations. Now, if we will discuss one by one. Low temperature tempering. First is the low temperature tempering. Here, only our heating temperature zone will change. That is 100 to 200 degrees Celsius temperature zone we are using here. Just we are taking the component at the end of hardening process. We are then heating it up to 100 to 200 degrees Celsius and holding there for 1 to 2 hours, and slowly cooling it up to room temperature. And this cooling is done in the air. This is the low temperature tempering process. Now, what exactly happens in this process, low temperature tempering? Now, in this low temperature tempering, whichever martensite is present at martensite is present, it will get decomposed at this 100 to 200 degrees Celsius temperature zone. During that, that martensite will get decomposed. Decomposed means it will get transformed to low carbon martensite, and some transition carbides are formed. Transition carbides are nothing but complex carbide compounds, iron iron and carbon compounds. Okay, like there will be just different combinations, like for cementite, or you can say that iron carbide formula is Fe3C. But here transition carbide means Fe 2.4 and one carbon atom, like this. Means these are the complex compounds. Some complex compounds or transition carbides will get formed here, and that martensite will get decomposed. Whichever martensite is there at the room temperature, after heating it to the 100 to 200 degrees Celsius temperature, it will get decomposed, and that will it will get transformed to tempered martensite. Tempered martensite. Okay, and due to this, what will happen here? Just what will happen here, during this process, the internal stresses are there whichever internal stresses are there that internal stresses created due to the sharp change in the temperature, that stresses will get eliminated. Okay, in the low temperature tempering, this will occur only. Internal stresses will get eliminated. Only internal stresses will get eliminated, and martensite will get transformed to tempered martensite or low carbon martensite, and some intermediate carbide compounds are formed. Just leave that intermediate carbide compound, that is for your information. Just you have to understand that here, whichever internal stresses are created due to the sharp decrease in the temperature, that internal stresses, or in short, you can say that whichever thermal stresses are created, that will get eliminated in this low temperature tempering. This is the first type. Then the second type is medium temperature tempering. Now here, just heating temperature zone will change 200 to 500 degrees Celsius. Now what will happen here? Now here, three changes will take place in medium temperature tempering. First will be same as that of low temperature tempering. That is, internal stresses will get eliminated due to transformation transformation of martensite to tempered martensite. Transformation of martensite to the tempered martensite. Internal stresses will get eliminated. That will be your first change. Then in the second change, whichever retained austenite is there, whichever retained austenite is there, that retained austenite, it will get transformed to bainite. It will get transformed to bainite, or that retained austenite, it will get transformed to martensite. Okay, here transformation will be like this. The first transformation, internal stresses will get eliminated due to transformation of that martensite to tempered martensite and some transition carbides. In the second transformation, retained austenite, it will get transformed to either bainite, or it will get transformed to martensite also. And whichever martensite is forming here, whichever martensite is forming here, then again it will get breaked, and it will form a mixture of ferrite and cementite at the room temperature. Ferrite and cementite is nothing but the pearlite. A ferrite and cementite mixture will be obtained at the end, that ferrite and cementite. And what we have achieved here, retained austenite is eliminated. Then next is whichever internal stresses are there, that also got eliminated. And at the end, whichever martensite is there, that has got transformed to mixture of ferrite plus cementite. Due to that, what happens here, it reduces the hardness and material becomes more ductile. Okay, all three purposes will be achieved in this medium temperature tempering. Retained austenite will get eliminated, internal stresses also get eliminated, and hardness will get reduced due to transformation of that martensite to the ferrite plus cementite mixture. This is the medium temperature tempering. Then the last tempering process is high temperature tempering. Just here again temperature zone will be different. For each type we have to explain like this. From room initially from room temperature component is heated at below A1 temperature in temperature zone 500 to 700 degrees Celsius, and that component is held at this temperature for 1 to 2 hours, and after that it is cooled to the room temperature in the air medium. This is for high temperature tempering. And what actually happens in this during this process, throughout this process. Now here what is the difference between medium temperature and high temperature tempering? Same things will or same transformation again occurs in the high temperature tempering. First will be internal stresses will get eliminated due to transformation of martensite into tempered martensite and some transition carbides. Then retained austenite will get eliminated. It will either get transformed to bainite or martensite, and whichever martensite is there, that martensite will get transformed to ferrite plus cementite mixture at the room temperature. Okay, same transformations are occurring in medium temperature and high temperature tempering. Just only single difference will be there at the room temperature. In both medium temperature and high temperature tempering we are getting ferrite plus cementite mixture, and the only one difference will be there. Cementite obtained in the high temperature tempering will be spherical in nature or spheroidal in nature. Okay, that is the only difference. Remaining transformations will be same, just temperature zone is different, and cementite obtained is the spherical in nature in the high temperature tempering. Okay, in this way these tempering processes are classified in low temperature, high temperature, medium temperature, and high temperature temperings. And these different transformations will occurs in the different temperature zone. Depending on the different temperature zones, different transformations are occurring here, and we will end up with the eliminated internal stresses, eliminated retained austenite, and that material will become more soft or some ductility will get improved. Now some proper with whatever property changes are occurring in this tempering process that are mentioned in this diagram, depending on tempering temperature, which is plotted on x-axis, and properties are plotted on the y-axis. Here it is mentioned internal stresses. You can see it from the curve. It will get eliminated in all three tempering processes. Internal stresses will get eliminated. Then hardness, it will get in low temperature tempering, hardness will remain approximately same, but in medium and in the high temperature tempering, hardness will get reduced. Okay, this is the high temperature zone, and this is medium tempering temperature zone. And then for the toughness, here you can see the toughness values. Toughness is increasing. Toughness is increasing for high temperature tempering and medium temperature tempering, and it is very less for low temperature tempering. So this diagram is indicating the effect of the tempering temperature on the properties of the steel component. Internal stresses will get reduced, toughness will get improved, and hardness will get reduced as tempering temperature increases. Okay, this is the effect of that tempering. Then one more small term is there that I will explain within 2 minutes only. Okay, this is just the graph of the tempering temperature and hardness. Okay, now here we are performing the tempering process to reduce the hardness, but in some kind of alloy steels, which contains some harder elements like chromium, tungsten, vanadium, molybdenum, what will happen instead of decrease in the hardness, hardness will increase during the tempering process. Okay, during tempering, why we are performing the tempering process? To decrease the hardness and to improve the ductility. But in some alloy steels which are having alloying elements like chromium, tungsten, vanadium, molybdenum, what will happen during the tempering process? Hardness is will get increased. Here you can see this. Hardness increased. Hardness is increased in the tempering process. And why it is happening? Due to formation of some alloy carbides. Due to formation and separation of some alloy carbides. This process will be termed as, or this such hardening process. Hardening means improving the hardness during tempering. Generally, we are performing tempering process for improving the ductility and decreasing its hardness. But here, in some kind of alloy steels, what is happening due to the alloy carbides, separation of these alloy carbides, hardening of that steel is occurring during tempering process. During tempering process, hardening is occurring. That's why this is termed as secondary hardening. This is termed as secondary hardening. Okay. During tempering process, hardening takes place due to separation of carbides, due to presence of this alloying elements like chromium, tungsten. It will be termed as secondary hardening process. Okay. And due to this secondary hardening, what will happen here? These types of steels will provide you high hardness even at 600 degrees Celsius temperature zone. It will provide you very high hardness at 600 degrees Celsius temperature zone also. Okay, so this is the secondary hardening. Okay, in this way, we have completed this heat treatment process. In today's lecture, we have completed retained austenite, effects of retained austenite, methods for elimination of retained austenite, then tempering heat treatment process. In that, we have studied its purpose, its procedure, then its types like low temperature tempering, medium temperature tempering, high temperature tempering, and then effect of the tempering temperature on the properties of the steel component. And at last, we have discussed one concept related to secondary hardening. What is the meaning of secondary hardening? Which is occurring in the certain type of the alloy steels. Okay, if you are having any query, you can ask me, or you can put that in the chat box. Or if you are not having any query, also mention that in the chat box. Please ask me if you are having any doubt. Please put that in the chat box. Okay, if all points are clear, uh, I will stop here. Thank you for attending this lecture. Thank you.